Okay, so good morning, everybody. We are going to finish today the chapter 1 concerning the course of stochastic calculus. So let's go. I open the virtual board. So during the previous session, okay, we have starting to study some properties of the Brownian motion. We have seen in particular that some transform of the Brownian motion are martingales with respect to the Brownian vibration. It was proposition 1.3.1. We have also seen together that if you have a continuous martingale starting from 0, such that all these quantities here are martingale, okay, for any theta, then necessarily this martingale is the Brownian motion itself. And we have studied, okay, the fact that if I transform in different ways the Brownian trajectory, I still obtain a Brownian motion, okay? So translation, okay, zoom, and here time inversion here. And we have used deeply this proposition 1.3.3 in order to prove the following. So typically we have studied some interesting property of the Brownian trajectories, proving that these trajectories are nowhere differentiable from the right and from the left with proba 1. We have also proved that the probability that the Brownian trajectory is monotonic in no interval is equal to 1. Okay, I think that's strange. And we have also proved, okay, we have studied the quadratic variation of the Brownian motion, proving that the quadratic variation of the Brownian motion on an interval of size t is simply equal to t, okay, the quadratic variation. And the fact that since I have a finite quadratic variation, then necessarily, okay, I have unbounded variations for the Brownian motion. Okay, so today we are going to continue the study. And typically, we are going to study the Markov property of the Brownian motion. We are going to give the definition of the geometric Brownian motion that we are going to see in the financial chapters. Okay. Then I will remind what we have done concerning the construction of the Wiener integral. Okay, and see what are the related properties. And we are going to see another example of construction of the stochastic integral. That will be the main part of the next chapter, but we are going to see some examples today in order to obtain the Ito formula for the Brownian motion, Ito formula for the Brownian motion that we are going to extend in the next sessions for general Ito processes. Okay. So let's start, okay? We have the following property for the Brownian motion that is called the Markov property of the Brownian motion. So we are going to do the computation, and you are going to see that it is very basic. In fact, it is based on the independence of the Brownian increments. But here, what I call Markov property, okay? So suppose, so you have the time here, okay? I have t, and I have s, okay? So for me, s is the present date. So t represents a future date, okay? And all what I have before t is what we call the past, okay? So what is the meaning of this proposition here? If you want to find the conditional expectation of f of bt, so at time in the future, given fs, so that is what happened before s, it is sufficient to compute the conditional expectation at the time s. It's not necessary to account for all the times before s, but only focus on small s. Okay, so if I want to express this property with words, okay, I can say that the future depends on the past only through the present date, okay? And it's what we call in general the Markov property. Okay, so let's do the this little computation here. It's a basic exercise. So I am interested in what? I am interested in computing the conditional expectation of f of bt given fsb. And I do this here for t strictly greater than s. So as usual, okay, we are going to make appear a part that is fs measurable and a part that is independent with respect to fs. So I make appear the Brownian increment bt minus bs. And so I have to add bs given fsb. And I am in the classical situation where I have here a part that is independent of fsb, and here a part that is fsb measurable. From what we have done together in the chapter 0, I know that the conditional expectation in this case is just a function of bs, okay, because I have independence here and measurability here. So at this stage, okay, I have already proved this equality here, that my conditional expectation is in fact just the conditional expectation given bs, because this conditional expectation only depends on bs, not on the Brownian motion at time strictly less than s. Okay. And what is phi of x? That phi of x here is simply given by an expectation. It is the expectation of what? F of bt minus bs plus x. Okay. And now it's not complicated to express this expectation as an integral, because I know what is the distribution of this one. This one follows the n x t minus s. Okay. So it means that I can express this expectation as an integral, okay, of f of y multiplied by the density of this Gaussian distribution here. So it is 1 over the square root of 2 pi t minus s exponential minus y minus x square over 2 times t minus s dy, okay? And so I have exactly this equality here, give me exactly what I have here. Okay, so the Brownian motion fulfills the Markov property, and I am able, okay, if I am able to compute this kind of integral, okay, to compute explicitly this kind of conditional expectation. So just a remark concerning the hypothesis of this proposition here. So I want f to be measurable, of course, and I suppose it to be bounded here. Why I suppose it to be bounded? In order to give sense to this conditional expectation here. But in fact, I can replace bounded here simply by f of bt belongs to L1, okay, something that is less restrictive, and that will allow me to obtain the result. Okay, so in order to give sense to this conditional expectation. Okay, so the Brownian motion is a Markov process. Okay, and you are going to see, and typically even in the next slide, that okay, this kind of reasoning is interesting, and typically for what we are going to do what we are going to do in finance. Okay. In this slide, okay, I defined what will be the stochastic process we are going to use in the financial chapter number 5. Okay, it's what we called the geometric Brownian motion. And in order to handle this geometric Brownian motion, we are going to do the exercise 1.3.1, okay? So just a remark concerning this definition. So what is the geometric Brownian motion and what is the idea below this geometric Brownian motion? First, the fact is that for financial applications, okay, we are going to use this process in order to model the price of a stock market, okay? The price is a positive quantity. So it means that in particular, okay, I can't use the Brownian motion in order to model a price because the Brownian motion is a Gaussian random variable, okay, at any time t. And so it takes positive and negative values, okay, with probability 1/2. So I can't use it in order to model a price. How to pass from something that is not negative to something that is positive and that is not positive to something that is positive. One possibility is to take the exponential of this quantity because I know that the exponential is always positive, okay? So it is just, okay, the strategy that you have below the definition of xt. So several remarks concerning this definition. First that, okay, it's very easy to generate xt with a computer. Why it's very easy to generate? Because I have explained to you how to generate a Brownian trajectory. And if you are able to generate a Brownian trajectory, if I give you x0, b, and sigma, you will be able, just applying this function here, to generate the trajectory of what we called the geometric Brownian motion. Okay? So very easy to generate using a computer. Okay? And in particular, it will be useful to have this nice property in order to compute prices using Monte Carlo approximation, for example. Okay, so I have this. What is more, I can remark that the logarithm of xt here is equal to what? So if I want to take the logarithm, okay, we are going to suppose that this one is strictly positive, okay, in order to make this quantity strictly positive and in order to be able to take the logarithm. Plus what? So plus b minus sigma square over 2t plus sigma bt. And I can remark here that the logarithm of xt follows a Gaussian distribution. Okay? So that's why we speak about, okay, a log normal process, because the logarithm of xt is Gaussian. Okay, we speak about, okay, log normal process. Log normal because the logarithm is Gaussian. Okay, so let's do the exercise, okay, in order to handle a little this one, okay? Okay, first question, show that xt exponential minus bt is a martingale. Okay. So what is xt exponential minus bt? This is equal to x0. So x0 here, okay, it's not totally clear in my definition. X0 here is a number, okay, is a number. It's a real number, okay, in this one. In particular, okay, if you see my exercise, these conditional expectations here and conditional variance are in my situation only expectation and variances. Okay, so you can erase this one, okay, and this one because it's the same in the case where x0 is a constant. So what is this? So it is this one, okay, and I have just exponential sigma bt minus sigma square t over 2, but I recognize this part. If I come back to the first slide here, or the second one, I know that all these quantities here are martingales. And typically it's what we have here. So it's a consequence of by proposition 1.3.1. Okay, so I have this. So for the small a, no problem. Xt times exponential minus bt is just a martingale. Okay. Second question. Compute the expectation of xt. Okay. So first of all, if I compute the expectation of xt, knowing that I have this term, okay, I can remove from the expectation all the terms that are so constant, that is here, typically x0, okay, exponential minus sigma square t over 2, and inside the expectation, we are going to have only this one, okay? And here, what we are going to use, but it's a classical result that you have to know from now on, okay, because we have used it a lot of time. That is, okay, if you have z that follows n m sigma square, if you compute its moment generating function, it is just equal to what? It is just equal to exponential u m plus u square sigma square over 2. And here, okay, my bt being n 0t, I obtain from this expression for this one, what I obtain. So the mean is 0, so I don't have this term. U is equal to sigma, and sigma square is equal to t. Okay, so I have exponential here, sigma square t over 2. And so I have a simplification between this term and this term, and I obtain that. So I have forgotten someone here. When I have written this here, okay, I have forgotten the part with the b. Okay, so I have here, okay, so we are going to erase. Here, you don't have simply x0, you have x0 exponential bt, this one, okay? So I have this, and then since I have simplification between these two terms, I obtain at the end, I obtain here this expectation that is equal to x0 exponential bt. Okay, so if I want to do a little plot of this, okay, I start from x0, okay, so if you suppose that, for example, I don't know, b is strictly positive, you obtain something like this for the expectation of xt, okay, so you have a positive exponential this way, okay, and when the case where b is strictly negative, okay, you will obtain something that converges towards 0, okay, but it won't be the case that we are going to be interested in finance, okay. So just a remark concerning this, so in expectation, okay, in expectation, xt has this behavior in expectation, okay, for b strictly positive. And what will be interesting is to remark that what is xt in fact? Xt is a part that is a deterministic part plus a part involving the Brownian motion, okay? So the Brownian motion here is the only source of randomness in this expression. So if I have a sigma that is very big, okay, it will put a big weight on my unique source of randomness. If I have a sigma that is very small, my source of randomness, okay, will be very small. So it means that the behavior of xt, okay, will be something that will be random around its expectation, okay, with the randomness that it's driven by the Brownian motion. So I will obtain, okay, something like this here for xt. So excuse me for the picture, okay. So we will have a tendency given by the behavior in expectation and around, okay, Brownian filtration, okay, and you have a plot of this one, okay, in the lecture's note at the page 46, okay. So you have something. So let's continue my computation here, okay. I want to compute now the variance of xt, okay, in order to obtain this term. So what is the variance? It's just the expectation of xt square, okay, minus the expectation of xt square. So I know this term, it is just x0 exponential to bt with a square here, okay. And as you can see, the term that you have here, the minus x0 square exponential to bt, is exactly what you have here, okay. x0 square exponential to bt with a minus 1 here, that is exactly the term I am interested in here. So if I want to compute the first here, let's compute this one. So what is this? Okay, but I just plug inside, okay, it is the expectation of what? Of x0 square exponential 2 bt minus sigma square over 2 t plus 2 sigma bt, okay. So once again, I can remove all the part that is deterministic from the expectation. Excuse me, it's not this one, okay. And I have to compute the expectation of 2 sigma bt. And once again, in order to compute this term, we are going to use this one for u equal to 2 sigma, okay, u equal to 2 sigma, m equal to 0, and sigma square equal to t. So I obtain here what I obtain. U is equal to 2 sigma, m equal to 0. So I have exponential, okay, 4 sigma square that is coming from u here, sigma square that is t over 2. And if I continue my computation here, maybe I have some simplification. So I have x0 square exponential 2bt, and I will have some simplification between the term here with the sigma square and this one. So what I have here, I have minus sigma square t, and here I have 2 sigma square t, and so I have here plus sigma square t. That is exactly the expression in green here. Okay, so I have proved the small b that the variance of xt is given by, okay, is given by this expression. Okay, it's given by this expression. Okay, so now it remains to prove that we have the small c, that is the geometric Brownian motion fulfills the Markov property. In fact, you are going to see that it's exactly the same methodology than the one used for the Brownian motion. Okay. So I am interested in this. And as usual, we are going to make appear a part that is Fs measurable and the part that is independent. To do this, we are going to do, so here keep in mind that in the case of the Brownian motion, in order to make appear the increments, we subtract something and then we add it, okay? Here we have, okay, an exponential form for xt, okay? So to do sum is not a good idea, okay? But we are going to do ratio here. So I will write for t strictly greater than s here. I will write xt as xt over xs times xs. Okay, so xs here is FSB measurable for sure. What is this one? Okay, taking the this expression here, I obtain simply. So this one is exponential b minus sigma square over 2 t minus s plus what? Plus sigma bt. Okay, and in fact, I remark that here I have bt minus bs and a deterministic part. So this part here is independent with respect to FSB. So I have a part that is independent, a part that is measurable, and we are going to use the proposition of the chapter 0 as usual. Okay, so I write it this way. And you will see that to the computation of price in the Black-Scholes model, okay, it's a little trick that we are going to use several times. So, okay, so what I know, my part is independent here, my part is Fs measurable, so it's a function of xs here, where phi of x is given by the expectation of f xt over xs time small x, in fact, okay, because xs is here. Okay, so this is the expectation I have to compute, and we are going to express this expectation, okay, using an integral. So let's do the job. So I remind that according to what I have written here, xt over xs is equal to exponential b minus sigma square over 2 t minus s plus, so sigma of bt minus bs, and this sigma by minus bt, and this sigma times bt minus bs, okay, as a distribution. So I can write it this way. It's a n0 t minus s, so I can write this random variable in distribution as this one, where j follows the n01. It's just because, okay, bt minus bs follows the n0 t minus s, okay? So when I want to compute this expectation, I have just to compute the expectation of this random variable where j is a n01, and so phi of x may be expressed as an integral with respect to the density of n01 excuse me, I have a problem with my pad, so I have okay, So it's technical issues I have to solve. So let's do the job. Okay. Excuse me, yeah. Okay, so now my iPad will be full of battery and I am able to continue without problem my course. Okay, so I have the density of n01 here, and I have to integrate, okay, the mapping related to this expression. So I have what? I have f of my x here multiplied by exponential b minus sigma square over 2 t minus s plus sigma square root of t minus s y. And I close the parentheses and you recover exactly what I obtained here for this conditional expectation. And you will see that in the chapter 5, when we are going to deal with the Brownian motion, this kind of conditional expectations here, this kind of conditional expectation will be related to prices of options, okay, written on the geometry Brownian motion. So in order to compute this price, we are going to be able to compute this integral. And in particular cases, it should be possible to compute explicitly this integral, typically in the case of the put and in the case of call options. Okay, so this little trick is important here because it will be used extensively in the financial part. Okay, so that's all for the moment concerning the geometric Brownian motion. Let's go to the next part. Okay, so now what we are going to do for the next, for the end of this session and the next two sessions will be, okay, to give sense. I want to give sense to this kind of quantities. Okay, so I want to give sense this. It's what we call to give sense to the stochastic integral. Also called the Ito integral. Okay, so my first question is, okay, why to define such an object is a problem by itself? Because all of us had followed some courses about analysis and even some courses about integration theory. So we have several ways to build integrals, okay? We have the Riemann integral, we have the Stiegler's integrals, okay? We have also the Lebesgue integral, and so on, okay? And my question is why this point of view can't be applied in the framework of the Brownian motion. So suppose that you are in classical analysis here, okay? So suppose that you are in classical analysis and that you have this object to define, okay? In classical analysis, so I won't enter into the details, okay, of what we are going to talk about now, okay, but if you want more precision, okay, you can have a look on the page 47 of the lecture's note, okay? So I said that there are nice situations where it is possible to give sense to this one, okay, in the framework of classical analysis, so F and J being mappings, okay? I said that if J is differentiable, no problem to define such an object, because in fact, what we call G of GS will just be G prime of S ds. Okay, so we have this situation where it will be possible to do the job. If J has bounded variations, it will also be possible to give sense to this integral, because in fact, we know from classical analysis that if I am a mapping with bounded variation from R into R, I can be written as the difference of two mappings that are strictly that are increasing. Okay, and in the case where J is increasing, it's easy to do the job, because intuitively, okay, suppose that you are continuous and increasing, for example, but you are more or less a distribution function. Okay, so if you are increasing, okay, and continuous, you are, let's say, a distribution function. So to define this integral will be just the integral or the expectation with respect to the distribution associated to this distribution function. Let's say this. Okay, so if you want more details on this topic, okay, it should be possible for you to have a look on the page 47 of the lectures note, okay, but what is my conclusion? If I want to apply classical analysis to build such an object, okay, is it possible to use this trick in the case of the Brown motion? No, it's not possible. Why it's not possible? Because we have proved together that the Brownian motion is nowhere differentiable from the right and from the left. We have seen that the Brownian motion is with proba 1 monotonic in no intervals. So I don't have the fact that I am increasing or not. And we have also seen together that the Brownian motion don't have finite variations. So you see that these three classical framework where in analysis we are able to build such an integral are not fulfilled for the Brownian trajectories, implying that it's not possible to use this classical ID in order to build a stochastic integral. So we need to work, okay, in using another point of view, okay? So the general answer to this question will be what we are going to do in the chapter 2. But today, we are going to study two particular situations. One we have already done, in fact, and one that will be new. Okay, so today, I will focus on this quantity. Where f belongs to L2 of 0 capital T. That is that here, we are not going to focus on integral of stochastic processes with respect to the Brownian motion, but just integral of mappings with respect to the Brownian motion. And in fact, it's a job I have already done, and I will remind you just after. It's what we have defined as the Wiener integral. But we are going to spend time just after in order to remind you what we have done, okay, in the beginning of chapter 1 when I have built the Brownian motion itself, okay? So in this case, okay, I have a nice way in order to build this integral, something that I have already done and something that you have on the slide here, but I will, okay, do more comment in a few minutes. And the second case we are going to study today, it's this one. So I have inside here, I will have inside a process, a stochastic process, but that have a very, very particular form. that is just to be a function of the Brownian motion itself. Okay, so today it's the two examples we are going to study. This one, because it is in fact directly linked to the construction of the Brownian motion itself. Okay, it's the notion of Wiener integral with a very nice property for this integral. Okay, and this one, why we are going to study this one before to study the general case, but because with this one we are going to have the Ito formula for the Brownian motion. Okay, so it's what we are going to do, now. Okay, and I will start with this one, and I repeat that if you come back to the last class we have done together live, okay, I have built the Brownian motion, and in order to build the Brownian motion, I have, okay, build in fact the Wiener integral using the argument of randomization of a Hilbert space. Okay. So let's do what happened for this case now. Okay, so I have this. So let's remind that together, okay, for f belonging to L2 of 0 capital T, we have defined two classes ago, okay, I of f that I have denoted, it's a notation here, notation. Integral between 0 and capital T of f of s dbs. I have defined this one as the sum from n equal to 0 to plus infinity of this quantity f key of n in L2 of 0 capital T multiplied by Gn, where the Gn are I, D, n01, and when Kn is an orthonormal basis of L2 of 0 capital T. And in particular, I can also express, because the scalar product here is none other than the integral of the product, I can write it this way. Kn of S ds multiplied by Gn. Okay, so it's what I have defined here as the Wiener integral. What we have proved together? We have proved that first that I of f is well defined, proving that this one, this infinite sum, okay, is convergent in L2. But we have also proved that this random variable is a Gaussian random variable with mean 0 and variance integral between 0 and capital T f square of s ds. We have proved that this mapping here is linear, and that I am able to compute the covariance between two Wiener integrals. The covariance between two objects of this type is just simply the integral between 0 and capital T of f of s gs ds. Okay, so we have proved all these things, okay, in the first session concerning the chapter 1 we have done together. It was the last session that I was able to do live, okay, in the room 170. Okay, so I have this. Okay. And keep in mind that why I have done this job at the beginning of the chapter 1, it was to define BT as I of the indicator function of 0t. So I have done the job this way, okay? And if I define BT this way, we have proved that BT here is a Brownian motion. And it's the construction I have proposed to you, okay, of the Brownian motion by randomization of my initial Hilbert space, that is L2 of 0 capital T, introducing, okay, a sequence of IID N01 that are the GN. Okay, I define the Brownian motion this way. So just a remark concerning notations here, okay? I can write it here. I have defined the integral between 0 and capital T of f of s dbs as I of f, defined this way. Of course, naturally, okay, what I will define as the integral between 0 and t of f of s dbs will just be the integral between 0 and capital T of what? I just put inside the indicator function, okay, of f of s dbs. And so it is just I of f indicator function of 0t. Okay, so it's exactly what I have written here, that I can define the stochastic integral between 0 and small t from my definition from 0 to capital T, okay, by using this, okay. And in particular, when I take f equal to 1, okay, of course I recover the definition of the Brownian motion if I take f equal to 1 here, okay. So we have for this Wiener integral a lot of nice properties that we are going to see together. And in fact, this Wiener integral process, okay, has almost all the same properties as the one for the Brownian motion. What we know that the Brownian motion starts from 0, has continuous trajectories, okay, as independent increments, okay, and that it is also a Gaussian process with a mean function equal to 0 and a variance covariance function that is equal to the minimum between the instants. The only hypothesis that won't be fulfilled by the Wiener integral with respect to the Brownian motion is the fact that we know that the Brownian motion is stationary in the sense that Bt minus Bs follows the N0 T minus S, meaning that the distribution of an increment only depends on the size of the increment you consider, okay? In the case of the Wiener integral, okay, it won't be the case. It will be the only difference between these two processes, okay? So let's have a look on this property. Okay, so for some of them, I have already done the job. For some of them, okay, we are going to do the job. And for some of them, I won't do because I want to do, okay, more proof in the chapter 2. So what I leave for chapter 2, so in green here, see chapter 2. In the chapter 2, I will explain why the Wiener integral is continuous. Okay, so keep in mind that when I have defined the Brownian motion, in fact, there is only one thing that I don't have proved is the continuity of the trajectory. Okay, if I come back to the definition of the Wiener integral here, if I want the continuity of the trajectory here, I have to prove that this infinite sum, okay, is continuous. What I have inside, of course, is continuous. And if I want to prove that the limit is continuous, I have to use, okay, classical result of analyzing, proving, for example, okay, the convergence uniform on each compact of this infinite sum, okay. It's a little bit technical and it's not the way I will do because, okay, in the chapter 2, I will have a nicer way to do the job, okay. So that's why I don't prove the continuity, nor in the case of the Brownian motion and in the case of the Wiener integral. So for continuity, I leave it for the chapter 2. And I will also leave for the chapter 2 that I have something that is adapted to the Brownian filtration, because it's something that is not that obvious, okay, with my previous definition. So for continuous and adapted, see the chapter 2 when I will do, okay, this for more and more general integrals. Okay. So what I will leave as an exercise? I will leave as an exercise the following. So exercise at home. The Markov property, because today I have started, okay, with 2 examples of Markov property. So you can do it at home to understand if you have understood what I have done in the previous slide. And of course, okay, make a peer increment. So you use independence of increments to do the job. Independence of increments. Okay, so for Markov property, the proof that this one is a martingale, I will leave you to do at home, okay? And for the other, we are going to do together, okay? So let's start from the first one to the last, okay? Except what I want to do and what I will do, okay, later on, and see what happens. Okay, so first of all, linearity. But the linearity, I have nothing to say, in fact. So I write in red what we are going to do together. Nothing to say because, okay, we know that f gives I of f is linear. So I have, by definition, the linearity of the Wiener integral, okay? So let's do the other. For the continuity, I leave it for the next chapter, okay? Central Gaussian process with covariance function equal to this one. Okay, why not? So I am interested here in integral between 0 and t of f of s dbs that is defined as I of indicator function of 0t f. Okay, so I have this. First, okay, the mean function and the variance covariance function. If I compute the expectation of this one, it is just the expectation of this term, and I know that this term follows a n0 integral between 0 and t s square of s ds by what I have done previously. So this one is 0. Okay, so the mean function, I am centered here. I am centered. For the variance covariance function, okay, since I am centered, okay, the variance covariance function here is just equal to the expectation of the integral between 0 and t, f of u dbu, integral between 0 and s, f of u dbu. Okay, and I know from what I have reminded previously that the covariance between two Wiener integrals, okay, is just, okay, between two capital I is exactly the integral of the product of the integrands here. So what I will have inside here will be just, okay, so here you have I of the indicator function of 0tf. Here you have I of the indicator function of 0sf. I will have here the integral between 0 and capital T of integral between 0 and t u f of u integral between 0 and s u f of u du. And this is equal to what? Okay, so I know that the product of indicator function gives the indicator function of the intersection. And here, okay, it depends on which one is the smaller. Okay, so in fact, I can prove that here, the indicator function of 0t multiplied by the indicator function of 0s is just the indicator function of the minimum between s and t. Okay, it's the mean between the two here. Okay, so I have exactly this one. And so I recover what I want, that is the integral between 0 and the mean between s and t of f square of u du. Okay, that is exactly to prove this result here. Okay. And now it remains to prove that I have a Gaussian process. If I want to prove, okay, statement B here, I have in statement B, Gaussian process. Okay, so what I have to do, well, for Gaussian process, okay, so what I have to consider, I consider T1, Tn belonging to R plus, oh, excuse me, to 0 capital T, and I consider lambda 1, lambda n belonging to R to the power n. And I know that a process is a Gaussian process if all the associated random vectors are Gaussian vectors. And so I am interested here in these quantities, the sum k equal to 0 to n of lambda k, indicator between 0, integral between 0 and tk of f of u dbu. And I want to prove that this is a Gaussian random variable. Okay, it's the definition of being a Gaussian vector and so of being a Gaussian process because I do the job for an arbitrary random vector made from the Wiener integral process. But what is this one? In fact, we are going to use the linearity, and by linearity, it's something that I can write I of the sum from k equal to 0 to n of what? Lambda k, indicator function of 0 tk f. And I know that necessarily this one is a Gaussian because I know this. I know that I of someone follows the n0 integral between 0 and capital T f square of s ds. Okay, so in particular, this term that I can express as I of someone, okay, follows a Gaussian distribution. Okay, so it's the job for small b. I have a Gaussian process that is centered and with a variance covariance function that is equal to the integral between the minimum between S and T, f square of u du. And of course, if you take f equal to 1, you recover the Brownian motion and you prove in this way that you have a continuous centered Gaussian process with a variance covariance function. If I plug 1 here, I obtain just the minimum between S and T. Okay, that is exactly the variance covariance function of the Brownian motion. Okay, let's do small c. So adapted, I have said that I will do it in the chapter 2. Okay, so I want to prove that I have independent increments, but that I am not stationary. Independent increments, but no stationarity. Okay, so what is the meaning of this one? Okay. So concerning stationarity first. I consider an increment. I suppose t is strictly greater than s. So what is an increment in this situation? But it's simply, okay, by construction integral between s and t of fu dbu, okay, that I can write as I of indicator function of st f. And I know what is exactly the distribution of this one. It follows the n0 integral of the square of this one, that is integral between s and t, f square of u du. And I see, according to this one, that in fact, I don't have a process that is stationary, because stationary means that this increment here has a distribution that only depends on the size of the interval st. But here I don't, or I depend on the size, but I depend on the size through this integral. And in general, okay, if you take the integral between 0 and 1, it won't be the same as the integral between 1 and 2 or the integral between 50 and 51, okay? So I don't have the stationarity here. So no stationarity because, okay, the variance of my increment depend not on the length of the interval, but on the integral between s and t, between the bounds of the interval of f u squared d. Okay. The only case where I am stationary, it's the case where I take for f a constant. Okay. And it's more or less the case of the Brownian motion. So the Brownian motion is stationary. It's a particular case of a Wiener integral when I take f equal to 1. And in this case, I am stationary. Okay. So I have this one. So now, if I want to prove that I have independent increments, so if I denote this one by x, my increment, okay, I have to prove that x is independent of, okay, FSB. Because my t is pretty greater than s. And I remind you that to say that x is independent of FSB, okay, it is equivalent to say that x is independent of all these quantities here. And what is my constraint? My constraint is that T1 and Tn has to belongs to 0s. Okay? So it is the meaning of being with independent increments in this situation. Okay, I want that my integrants, okay, is independent of any Gaussian vector made of, okay, the process at instant that are less than s. Okay, So I am interested in this one. I will write it this way, okay. But, and this one that is just the integral between S and T. Okay, what I have here? But I have the fact that here you have a Gaussian vector because the Wiener integral process is a Gaussian process. So here you have a Gaussian vector. Okay. And I know it's an exercise we have done in the chapter 0. We know that in order to prove that the first component of a Gaussian vector is independent of the random vector made with the other component, in order to prove this, it is sufficient that the pairwise covariants are equal to 0. Okay, so if I compute the covariance between x and the integral between 0 and ti, what I obtain, so here it's the integral between s and t. So I have, in fact, I am able to deduce, okay, it will be gamma. No, excuse me, it's not, it won't be gamma, but something that is not very far. It will be, okay, the covariance of what? Of I indicator function of STF and indicator function of 0 TIF. But I know what is this term here. I know what is this term because I have reminded to you that capital I fulfilled this, in particular that the covariance between two capital I is given by this expression, that is the integral of the product, But if I come back to my case here, what is the integral of the product? So the product of this term and the product of this one, but I have here indicator function of intervals that are disjoints, okay, or with a single point inside that may be S, but whatever, okay. So the integral of the product of this mapping is just equal to 0. So the covariance of the first component with the other is equal to 0. Since this vector is a Gaussian vector, we know from a result, okay, concerning Gaussian vector seen in the chapter 0 that I have independent increments, okay? So if you have a look on the proof I have done to prove that the Brownian motion is, okay, defined as I of the indicator function of 0t, it's exactly the same proof I have done. Okay, exactly the same proof I have done. Okay, so I continue. So for small d, I want to do the proof because why I want to do the proof so for small d? If I take two Wiener integrals of this type here, okay, this one may be written as capital I of indicator function of 0t multiplied by f. Here, this one I have capital I of the indicator function of 0u multiplied by j. I know from what I have just used previously that the covariance between two capital I is known, and using this result, I will obtain, okay, that this covariance here is equal to the integral of the product, that is the integral of the product of the indicator function that give you the minimum here, multiplied by f and j. Okay, so nothing new. This one, okay, is just a consequence of the fact that covariance of I of the mapping f1 and I of f2 is equal to the integral between 0 and capital T of f1, f2. Yes, okay. I have simply this here. So I leave you this one for you to do at home, okay, and we are just going to prove that, okay, the Wiener integral process is a martingale with respect to FTB. And keep in mind that if you take f equal to 1, you recover the Brownian motion, simply the Brownian motion. Okay, so let's do the job here. Okay, so I do this. So I want to prove this, that this one is a martingale. Okay, well, let's do the job. Okay, what I want to do, I am interested in this. Okay, and I want to prove that it is equal to this term. It's the martingale property. Okay, it's the only thing I have to prove because I know that here you have random variables that are integrable because they are Gaussian. Okay, so it's the only thing I have to prove in this proposition. So let's do the job. But once again, we are going to make appear increments here. So what is this? I write, in fact, the integral between 0 and t as the integral between 0 and s of f of u dbu plus the integral between s and t. Okay, so I have a part here that is fs measurable. Okay, so I can remove it from the conditional expectation here because it is fs measurable. And here I have a part that is independent of fsb. So the expectation in the case of independence is just, the conditional expectation in the case of independence is just the expectation. The expectation here that is simply equal to 0. So I have proved my martingale property. Okay. So here with this proposition 1.3.9, okay, what I have done, I have extended, okay, all the things we have seen in the case of the function. There is only one thing that is missing, that is with this process, we don't have the stationarity. But if you take f equal to 1 in this proposition, okay, you recover all the properties of the Brownian motion we have seen together. Okay. So do at home, okay, this one, okay, it's a good exercise in order to handle the property of the Wiener integral and also prove the Markov property. What you will do, but you will do exactly the same transform of this one, that is to appear increments because the increments are independent in this situation. Okay, so we are going to do to finish the part concerning Wiener integral, okay, and after I will do a little break in order to have a coffee. I want to finish with a proposition that is more an exercise, okay? So what is the meaning of this one? For the moment, we have to this integral between 0 and t of f of s dbs for f belonging to L2 of 0 capital T. So the only condition I impose on f is to be square integrable with respect to the Lebesgue measure on 0 capital T. Okay, I need no irregularity for small f. In this way, okay, in this situation, we have defined this one as I of indicator function of 0t f. So it means that the Wiener integral is defined as a random variable. I don't give you what are its values. I don't know what is the value of this one at W, at a particular W. Okay, in my definition, I just define the Wiener integral, okay, as a random variable. I don't define, okay, what are the trajectories of this process. I just say that for any fixed t, this integral fulfilling a known distribution that is in this case a Gaussian one. Okay? The aim of the proposition we are going to prove here, the proposition 1.3.10, is just to tell you that in the case where you impose more regularity on f, that is here you have f that is in L2, if you impose it to be of class C1, then this integral here may be defined basically, okay, W by W. In the sense that you see that once we will have proved this equality here, this Wiener integral is just, okay, something that may be expressed very basically from the Brownian motion itself without a complicated formula, okay? And so I can deduce what are the trajectory of this one from the trajectories of the Brownian motion. But of course, the price to pay is that to write this equality, I need this one to be regular, okay, in the case that, in the sense that I have to take f of class C1, okay? So we are going to see what happened for this equality now, okay. So I want to prove the equality in blue. Okay, so to do this, we are going to remark the following. So keep in mind that the integral between 0 and t of f of s dbs is defined as an infinite sum. Time Gn, where the Gn are IID and 0, 1, and where the key n are an orthonormal basis of L2 of 0 capital T. Okay, it's the way we have defined, okay, the left part of this equality. So we are going to handle this term here. We are going to handle this term, and to handle this term, we are going to use the fact that f is of class C1, saying that in fact, okay, what is f of s? F of s, okay, may be written as, okay, but the integral of the derivative, in fact, so I can do this in this way, integral between, so, excuse me, I'll write it this way. So the idea is to express this quantity here using the derivative, because I have a derivative inside, and I use the fact that I am C1, and I can say that, okay, you know that the integral between s and t of f of u prime du is just equal to ft minus fs. Okay, so I have this. Okay, so in other words, I can say that the term I am interested in, okay, can be expressed as the integral between 0 and t of f of s, but f of s is equal to what? It is equal to ft minus this integral. Okay, so I have a minus here. Integral between s and t, f of u du, okay, kn of s ds. So fs is equal to ft minus the integral, so it remains to prove here, plus, or to write, plus ft, the integral between 0 and t of kn of s ds. So I repeat that I have a minus here. This term is equal to this one because I use the fact simply that I am able to compute the integral of the derivative. So I have this, okay? So here you see that you have ft, that is the ft that will appear here. And here, if I do the sum of this term multiplied by gn, okay, will make appear here. This one will allow me to obtain this one. Okay? The minus here will be this minus, and I have to prove that I have this equality. So here I see for the moment that, okay, excuse me, there is a prime here. Of course, there is a prime here, the integral of the derivative here. So I have this one. So I don't have, okay, exactly or typically this expression here, but we are going to use an integration by part here. If I denote this one by h of s and this one by j prime of s, using integration by part formula for this one, okay, I will express this quantity as, okay, as what? As so I see that this one at small t, okay, so let's write the integration by part formula. Okay, so I will have what? Okay, this one that is equal to I have a minus before, okay, and I apply my integration by part. So I have h of s, g of s between, okay, 0 and t minus, okay, minus 1, minus what? Minus the integral between 0 and t of what? So of the derivative of this one. What is the derivative of this one with respect to s? It is minus f prime. So I have a plus here, and I have f prime of s kn of s ds. Okay. No, excuse me. Write nothing. I need a break, so I just finish this one, and after I do a little break. So I have, let's write it correctly. I have my h here. Okay, so my h prime of s is equal to minus f prime of s. Here, the primitive of this one, okay, my j of s will be the integral between 0 and s of Kn of u du. Okay, so when I compute the derivative of this one, I obtain exactly what I have here. So if I use to compute this term, the integration by part formula, it's f times j I have to take between 0 and t plus the integral of the derivative of h that is equal to minus f prime. That's why I have a plus here. And j, that is the integral between 0 and s of Kn of u du, and here I have my ds. Okay. What I obtain for this term? At time t, ht is equal to 0. So for small t, this term is 0. And at 0, what happened? At 0, it is this one that is equal to 0. J0 is equal to 0. So you have a term that is equal to 0 here. And finally, what I obtain, that the integral between 0 and t fs Kn of s ds is equal to what? So I use what I have obtained here, and yes, I have plus here this term here, the term in green, plus the term in green here, this one. Okay, so I obtain this integral that is equal to minus the integral between 0 and t of f prime of s integral between 0 and s Kn of u du ds, that is this term here, okay, with the minus that comes from this one, and plus the term in green, that is this one here, plus f of t integral between 0 and t, okay, of Kn of s ds. And it's almost finished now. Why? Okay, so let's do the job here. It's almost finished because what I have, so I erase my computation. You have it on the previous slide. So if I consider, so I have this integral that is given by the infinite sum, and I have expressed this term inside as this one, okay? So I can copy what I have written here, okay, to make it clear. So the integral between 0 and t of f of s Kn of s ds is equal to what? Minus the integral between, so we'll let small place here in order to modify just after, okay, write it this way. So ds, that is equal to what? To minus the integral between 0 and t f prime of s integral between 0 and s Kn of u du, and I put my ds here, you are going to understand why just after, plus ft, the integral between 0 and t Kn of s ds. But what we are going to do here, I want to make appear this infinite sum, so we are going to consider the finite sums. This one, and I have to multiply by Gn here. I do the same here, and by linearity of the integral, I can write here this one, because here I have a term that doesn't depend on small Gn. Okay, I have this term inside here. And here I have the sum from n equal to 0 to capital N of this one, Gn, because once again, here I have something that doesn't depend on n. What I have here, I have simply that this one converges toward exactly what I call integral between 0 and t f of s dbs. This one converges toward the bt, simply. It's the definition of this one for f equal to 1. Okay, so this one goes to bt. And I have inside here this one that converges toward bs. And so you have exactly this expression that the integral between 0 and t of f of s dbs is equal to ftbt minus the integral between 0 and t of f prime of s bs ds. So you have proved this relation in the case where f is of class C1. Okay? So just let's have a look that, okay, it implies this, that when f is regular, you can define the Wiener integral w by w, okay, using the Brownian trajectory. But unfortunately, if f is not regular anymore, I can't write this equality here that is just based on an integration by part formula. And you will see later on that this little equality here is just a special case of the Ito formula, okay, for stochastic processes, or something that I will also call the integration by part formula for stochastic processes. But unfortunately, as I have said, okay, when f is not regular enough, okay, but I don't have this formula, and the Wiener integral is not defined w by w, but defined as a random variable. Okay, so let's do a little break, and I will continue in a few minutes, okay, concerning the other case of the integral I want to do today. Okay, so let's continue with the course. Okay, so let's come back to the virtual board. Okay, so we have finished with the Wiener integral, and now the objective will be to handle. So it's a second case, and you will see that in the chapter 2 I will do the general case that will extend both the Wiener and this one. Okay, so I want to give sense to this kind of integrals. So here I have a very particular stochastic process here that is just a function of the Brownian motion itself. Okay, the function of the Brownian motion itself. So let's see the following proposition. So the proposition is in fact the definition of this. Okay, the definition of what is this object. So what is the definition of this integral? If so, I have a condition f in order to be able to define the integral this way. If I suppose it f to be differentiable with bounded derivative, then this sum is in fact convergent in L2, and we denote its limit in L2 by this one. Okay, so I copy what is in the definition. So if I suppose f differentiable with f prime that is bounded, the integral between 0 and t of f of bs dbs is equal to the limit when n goes to plus infinity. So it's the limit in L2, okay, of what? Of this sum. F b t I over n b t I plus 1 over n minus b t I over n. Okay, so we have this. Okay. So several remarks. First, a priori in this proposition, I have to prove something. I have to prove the convergence in L2. But I will suppose it for the moment because I will prove, okay, a more general result in the chapter 2. Okay, so for the moment, I admit this proposition. That is, I admit the convergence in L2 of this sum here. Okay, and I will prove in the chapter 2 that this sum is convergent in L2. Second remark, in the case of the Wiener integral, okay, so in the case of the Wiener integral, that is the case where I deal with the integral between 0 and t of f of s dbs with f that belongs to L2 of 0 capital T. We have seen that here we have a Gaussian with mean 0 and with these variance here. Okay, it's a square here. Okay. Here, first remark, okay, it's the remark I have written here. In general, this limit, okay, this limit here is not a Gaussian random variable. This limit is not Gaussian in general. Why? But because here, okay, so okay, I have something that is Gaussian here. It's the Brownian increment. But here, I don't know the distribution of this one. I don't know the distribution, implying that for the limit, a priori, I am not Gaussian anymore. Okay, I don't know if I am Gaussian, and a priori, I am not Gaussian anymore. Okay, so we are going to see an example of such a computation here to prove you that, in fact, this what is not Gaussian in general. So let's do the example of the bottom of the page here, that is to compute this one. Okay, so it means that I want to do the job for f equal to identity. And of course, identity is of class C1, okay, it's of class infinity, in fact, and the derivative is equal to 1. So I have something with a bounded derivative. Okay, I have something with a bounded derivative. So I have the right to apply this proposition. Okay, so if I want to compute the integral between 0 and t of bs dbs, by the definition implied by the proposition here, it is what? It is the limit when n goes to plus infinity of what? Of the sum from I equal to 0 to n minus 1 of f being equal to the identity, I have just bti over n here, and I multiply by bti plus 1 over n minus bti over n. Okay? So I have this term to handle. And the idea, okay, is to be able to find the limit in L2 of such a quantity. And you are going to see that we are able to compute the limit of this sum, okay, from one thing that we have done previously. First of all, okay, just remark that we have the following. I have the following identity here. If you have a number a and that you multiply it by b minus a, then I can write this one as 1/2 of b square minus a square minus b minus a square. It's an obvious equality that comes from the fact that, okay, you obtain this one when you develop the square here. You have b square minus 2 times ab plus a square. And if you do the difference between this one and this one, you recover exactly this one. Okay? So if I apply this little identity to what I have here, because I have exactly something of this form here. I have the a here, and I have here b minus a. Okay? So what I am interested in here can be written this way. So the sum I am interested in, okay, that is the sum from I equal to 0 to n minus 1 b ti over n b ti plus 1 over n minus b ti over n. I can write it as 1/2, the 1/2 coming from this expression here. Then I have the sum of the difference of the square. So it is the sum from I equal to 0 to n minus 1 of b ti plus 1 over n square minus b ti over n square. And then I have minus the sum of the square of the difference. B ti plus 1 over n minus b ti over n square. So if I want to find the limit in L2 of this one, I have to find the limit in L2 of this sum and of this sum. Okay? What happened for the first sum? But for the first sum, it's easy because here I have simplifications, okay, when I compute the sum of this term, because you have different, okay, and you have simplifications between successive terms of this sum, and I obtain at the end only, okay, this term for I equal to n minus 1, that is exactly bt square, and minus this term for I equal to 0, that is b0. So I have simply bt square for this expression here. Okay, so this one, in fact, I don't have to compute the limit because it is equal to bt square. And what is the limit of this one? But here you recognize the quadratic variation of the Brownian motion over the interval 0t. And we have proved together that when n goes to plus infinity, okay, when n goes to plus infinity, this integral here converges toward the length of the interval on which you take the quadratic variation. I remind you the result. It was the result we have proved at the end of the previous session. That is this one. Okay, if I consider the quadratic variation here, the quadratic variation, it converges toward t almost surely and in L2. So it was for this particular subdivision, but keep in mind that I have said to you during the previous session that when you have a step size in the subdivision that converges towards 0, I have always the convergence in L2. And when I have a step size corresponding to a sum that is finite, then I have the almost sure convergence. Okay, it was my last remark at the end of the previous session. Here, if I take as a subdivision tj over n, this one goes to 0 when n goes to plus infinity. And in fact, if it goes to 0, it implies that I have the convergence in L2. That is exactly what I want in the limit I want to compute here. So I am here. That is, this term converges toward t when n goes to plus infinity. Okay? And if I summarize, okay, what I have obtained here, I have obtained that the integral between 0 and t of bs dbs is equal to 1/2 of bt square minus t. Okay? In particular, I have something here that it's not Gaussian, because you have in this expression the square of a Gaussian. So something that is a chi-square distribution here, but that is not a Gaussian distribution. Okay? So I have this one. We are going to do 2 remarks concerning the computation we have done here. First remark. In fact, this construction is not that unnatural. It's not that natural because keep in mind that if you have a mapping F, okay, from 0 capital T into R, the way you define the Riemann integral so the Riemann integral, as you know, may be defined as the limit of the Riemann sums. And how to compute the Riemann sum here? I consider regular subdivision with a step size that is equal to t over n. And I obtain this way the sum of f ti over n, ti plus 1 over n minus ti over n. Okay, it's the limit when n goes to plus infinity. And you have here the Riemann sum. And you see that my definition here is not that far, because this term here is in some sense analogous of this one, but instead of having here the size of all the intervals of my subdivision, I replace this increment here, that is just the size of my interval, by the Brownian increment on this interval. So if you want, in some sense, okay, the way I define the interval, this integral here, is just a generalization of what happened for the Riemann integral, okay? Keeping in mind that I replace the increment over the bounds of the interval, that is just the length of the interval here, that is this one is t over n, by the increment of the Brownian motion, okay? So this is not that unnatural to do this. A remark that I can say is that keep in mind that when you have the Riemann sum theorem, so here I have chosen here this point to be this one, that is the lower bound of my interval. But you know that the Riemann sum theorem works also if instead of choosing the lower bound of the interval here, I choose any point here, any point, excuse me, any point in my subdivision that I denote by x, I, n here. Meaning that if in this Riemann sum I replace f of ti by f of x, I, n, I have the same convergence. So in the Riemann sum theorem, okay, the only thing I need to have is to take a point between these two bounds, okay, in a large sense. In general, we take the lower bound, but if I take a point in the interval here, typically I have the same thing. And typically it's what happens if I take, for example, for xi of n, the middle of the interval. It's something that gives me, again, okay, what I want. Here, so in this definition here, you see that I choose bti over n, okay? And the natural question is to say that, okay, is it possible to do the same as in the case of the Riemann sum? That is, instead of taking b at the lower point of the interval, take b at, in fact, any point, something like this, okay? But the answer is no, in fact. The answer is no, because but if I take the bti over n here, it's not a choice that is innocent. Because when I do this choice, okay, I have this random variable, bti over n, that is independent of my increment bti plus 1 over n minus bti over n. So I have independence here between these two random variables. And the fact that I have independence will be very important for what I want to obtain after. It's this key assumption that make the things work in this particular situation, okay? So it's not possible for me to take any thing I want inside here, contrary to what happened for the Wiener integral. So let's see this on an example. So I have defined the integral between 0 and t of f of bs dbs as the limit in L2 this here. Okay, I said that in the case of the Riemann integral, I can choose any point in Ti over n, Ti plus 1 over n, okay? And what we are going to see now is that in this case, Bti over n is independent of this increment. And if I choose, okay, any point in the interval Bti over n, Bti plus 1 over n, I lose, okay, the definition of the integral. So let's see, for example, what happened for f equal to identity. And if instead of considering this sum, so Bti over n here is this point that may be considered as the lower bound of the interval Bti over n, Bti plus 1 over n, or the upper bound, it depends because I don't know which one is the greatest here, but one bound of the interval. And let's see what happened if I compute, instead of computing this sum here, I replace Bti over n by the middle of these 2 points here. That is, I replace Bti over n by Bti over n minus b, or plus, excuse me, Ti plus 1 over n, and I consider the middle, okay, of the increment. In this situation, you see that I have an identity that I know I have a plus b factor of b minus a. Okay, so this sum here is 1/2 the sum from I equal to 0 to n minus 1 of what? Of b, okay, Ti plus 1 over n square minus b Ti over n square. And at the end, okay, it's not necessary to compute the limit in this situation because I have immediately bt square over 2. So this sum is equal to bt square over 2. And keep in mind that what I have computed by myself is that the integral between 0 and t of bs dbs is equal to 1/2 of bt square minus t. And you see that these two quantities are different, okay? And what is the meaning of this? It means that in my definition, in my previous definition here, the choice of Bti over n here is very, very important because Bti over n is independent of this increment. So we are not like in the situation of the construction of the Riemann integral where in this interval here, Ti over n, Ti plus 1 over n, I can take as a point inside f here any point I want. Here in this situation, I can't take any point between Bti over n and Bti plus 1 over n. I have to take Bti over n if I want to cope with this definition. If I change Bti over n here by a point between Bti over n and Bti plus 1 over n, in general, I lose the definition. And it's exactly what I have proved here. If instead of taking Bti over n, you take the middle of these 2 points here, that is Bti over n plus Bti plus 1 over n over 2, I obtain something in this situation, but something that is different to the integral I have defined previously. Okay? So be careful. In my proposition, this definition is important. If I change this one into another b, it doesn't work. Because here, in fact, I have independence between this one and this one, a point that is fundamental, that will be fundamental in the following. Okay. Second remark concerning what I have obtained here. We have obtained together this formula. Integral between 0 and t of bs dbs is equal to 1/2 bt squared minus t. Okay, so I said that this formula is not that natural. Why this formula is not that natural? Because we have in general the following. Okay, so if I am in classical analysis, okay, with capital F, that is C1, and if I take a stochastic process GT, that is also C1, that is with C1 trajectory, I can write the following equality. F of GT is equal to F of J0 plus the integral between 0 and t of F prime G of S, G prime of S, ds. Of course, I have this because here it's just the derivative of this expression that I can consider, okay? And the integral of the derivative give me the difference between, okay, t and 0 for this mapping here. And this integral here is something that in classical analysis I can denote by the integral between 0 and t of f prime g of s d of gs, okay, because here my j is regular. Okay, so this is a classical formula that you use, okay, every time in classical analysis. In particular, if I take f equal to x squared, so if I take f of x equal to x squared, this formula here becomes gt squared minus g0 squared. And if g0 is equal to 0, I have 0 here. That is equal to the integral between 0 and t of 2g of s g of gs, implying that if this one is equal to 0, okay, if I start with a process, okay, starting from 0, I have the well-known formula, that is this one, the integral between 0 and t of gs d of gs is equal to gt squared over 2. And you see that the formula that you have here is not the same kind of formula that the one we have here. We have an extra term here. That is this term, that is an extra term. So we don't have the usual formula, okay, the one that we have for regular processes, okay, in the case of the Brownian motion. And the explanation is that, okay, but the Brownian motion here is not C1. I know that the Brownian motion is nowhere differentiable from the right and from the left. Okay, so I don't have such a formula because the Brownian trajectory is not regular. And in particular, okay, as you see, if my mapping here is regular, I know that it has a quadratic variation equal to 0 because it has bounded variations. Okay, so the quadratic variation is equal to 0 in this case where my trajectory are regular. In the case of the Brownian motion, we have seen that the quadratic variation, okay, are finite and equal to the length of the interval. And you have here exactly the quadratic variation of the Brownian motion over the interval 0t. Okay, so this extra term comes from the variation, the quadratic variation of the Brownian motion that is not 0, that is the length of the interval, contrary to what happened for something that is regular. Okay, so I have some rules of computation for these integrals that are not the one that I have used classically in classical analysis. I have an extra term that comes from the quadratic variation of the Brownian motion. And typically, the extension of this formula, okay, here, is what we called the Ito formula for the Brownian motion that we are going to see now, and we are going to finish with this one today. So I erase this one, yes, and I keep this formula. Okay, I have some hypothesis for this Ito formula for the Brownian motion. Okay, I have an hypothesis. I suppose F to be of class C2, okay, twice differentiable, okay, with derivatives that are continuous. And I suppose that I have a bounded second derivative. Then I said that I have the inequality in red, that is f of bt equal to f of b0 plus the integral between 0 and t f prime bs dbs. So this one here, the beginning of the formula here, this term here, it's exactly what I obtain here. It's the beginning. F of gt is equal of f of j0 plus the integral between 0 and t f prime of gs dgs. Okay, so we have for the Brownian motion the same beginning, but we have this extra term here that is equal to 1/2 the second derivative, the integral between 0 and t of the second derivative of bs ds. Okay, so it's here the new term with respect to classical computation. Okay, and I just say that in blue, okay, it's just a compact notation in order to write this equality. I said that d of f of bs, that is the variation of this one, is equal to what I have inside here plus 1/2 of what I have inside here. Here it's just a notation, a differential notation in order to express in a shorter way the fact that, okay, we have this integral inequality. Okay, so this one, I will use this one or this one in order to express, in fact, this equality. So just a remark, in fact, two remarks before to do the proof or the sketch of the proof more, okay? Because, okay, with the virtual board, okay, I'm not sure that I will do all the computation in all details, okay, but I will see. Let's see. This one. So two remarks. First, why f C2 with f second bounded? So if you see this formula here, I have two integrals, okay? So I have this integral here, so the second derivative is bounded, so it's just the integral of a continuous mapping, okay, with f second that is bounded, so no problem. So this Riemann integral here is well defined because f second is continuous and the Brownian trajectory is continuous, okay? For the first integral, okay, I have this one, f prime of bs dbs. Why it is well defined? But it is well defined because keep in mind that in my definition, in order to define this one, I want that the mapping f here is differentiable with a bounded derivative. But here, what I have here f prime. So in order to cope with the previous definition, f prime has to be differentiable with bounded derivative if I want to use my previous definition. But what is the fact that f prime is with bounded derivative? It's just that f second is bounded, okay? So I need this hypothesis if I want to be able to define this term, okay, using the previous proposition, okay? So this hypothesis is just to be able to define, okay, this term in a correct way with respect to what I have defined previously. It is my first remark. Second remark. What happens if I take f of x equal to x squared? So x squared fulfills my hypothesis because f prime of x is equal to x, and f second is bounded because it is equal to 1. Excuse me, it's 2x here. Here it's 2x, and here I have 2. So if I apply this formula to this case, what I have bt squared that is equal to b0 squared that is equal to 0, plus what? 2 times the integral between 0 and t of bs ds plus 1/2 of what? Of the integral between 0 and t of the second derivative being equal to 2. So I have here 2t. And this implies that the integral between 0 and t, oh, excuse me, it's the bs here of bs dbs is equal to what? It's equal to bt squared minus t over 2. And keep in mind that this formula, it's exactly what I obtain, okay, here in my computation, in my direct computation involving the quadratic variation of the Brownian motion. So it means that the Ito formula here expressed this way is just a generalization of the formula that I have proved directly, okay? It gives you, okay, a decomposition of f of bt in terms of a constant, a stochastic integral, and a Riemann integral, okay, when f is sufficiently regular, okay? So now what we are going to see together, okay, so I want to show you that in fact the proof is not that complicated of this one, okay? The proof is in fact simple. So just 1 minute because I have a problem with my pen, okay? I just want to solve it, okay, if it's possible. So it's not, so I will do after, whatever. Okay, so let's do the proof of this one. So maybe I won't do the whole computations, but I will do the more important part. And typically I want you to understand the philosophy of this proof. First of all, we are going to have a look on the way this one are defined. Okay? So I have defined from the previous proposition the integral between 0 and t of f prime of bs dbs. It was defined as the limit in L2 of these quantities here. B T I over n, B T I plus 1 over n minus B T I over n. It's the way this integral is defined here. For the second integral here, it's a Riemann integral. So I can define it as using the Riemann sum theorem, and it will be the sum from I equal to 0 to n minus 1 of what? F second of B T I over n, T I plus 1 over n minus Ti over n. And in fact, you can prove that the convergence here is a convergence almost sure And since f second, this one is bounded, I can pass from the almost sure convergence that is given by the Riemann-Sum theorem to a convergence in L2. Okay, so both integral here may be defined as limits in L2 of sums, involving in the first case increment of the Brownian motion, involving in the second case, okay, increments in the classical sense. Okay, and I want to prove that f of bt minus f of b0 is equal to this limit plus 1/2 this one. Okay, so first of all, I see that in the definition of my integrals, I have a discretization that I've involved. Okay, we are going to make appear the discretization. And the way we are going to do this is simply to write f of bt minus of f b0 as the sum from I equal to 0 to n minus 1 of what? Of f b, okay? So I can write it this way. So if I sum from I equal to 0, I will write it this way. So here I will have b t I over n, and here b t I plus 1 over n with a minus here. Because, okay, when I do the sum here, I have a diagonal simplification between this term that will give me f of bt, that is this one for I equal to n minus 1, and this one that is this one for t equal to 0, or for I equal to 0. Okay? So why I do this? I do this because in this way I make appear increments that are involved in these limits here. Okay? So I want to pass from this difference here to, okay, make appear by something that is in relation with the derivative. And in this way, we are going to use the Taylor formula. The Taylor formula tells me that, so I apply the Taylor formula for f. F is C2 with bounded derivative. Okay, so I am C2, so I can apply the Taylor formula at D. So Taylor formula for f, that is C2, and between the points, b t I plus 1 over n and b ti over n. Okay? So what I obtain if I do this? So f b t I plus 1 over n, okay, that is equal to f of b t I over n plus f prime b t I over n b t I plus 1 over n minus b t I over n plus 1/2 the second derivative of what? So just let me 1 second to precise what I have here. bti over n here square. And you have here a point that I can call C of I and n, where C I n is between b t I over n and b t I plus 1 over n. So here it's the exact Taylor formula, for f applied at the point bti over n and bti plus 1 over n. Okay, so I have this one. So what I have to do now, so I will continue in the next page, but I can see things for the moment. Okay, so I have to do sums of these increments. So I have to do sums of this term, but I see that the sum of this term will be exactly what I will have here. The sum of these terms, so here you have exactly what you have here. Okay. For this one, it's not exactly what I have here, but I will have to work a little. But what I know is that here I have a 1/2. That is the 1/2 that appear in my formula here. And I have something involving the second derivative as here and as here. Okay. So I can see that I am not very far, in fact. Okay. I am not very far. So let's continue in another page. So what I will do, so yes, maybe I will do this way. This way, copy one, tac, tac, and I erase few things. Okay, I will erase. So I keep the definition for the moment. Okay, and I will just write what I obtain here, that fbt minus f of b0 is equal to what? It's the sum from I equal to 0 to n minus 1, f prime b ti over n, b ti plus 1 over n minus bti over n. So this is the term coming from this increment here. So I erase this one. And it remains here. So I have a term in blue. I have a term in green here, plus 1/2. Okay, the sum from I equal to 0 to n minus 1, f second oxy I n, and the increment here b t I plus 1 over n minus b ti over n square. Okay, I have this one. Okay, so I erase this one. Okay. The first thing I can remark is that the term in blue here, that is this one, converges toward this term. So the term in blue one, that is this one here, converges toward this term in L2 when n goes to plus infinity. So it means that I have the beginning of my Ito formula, okay, because this first sum here converges toward the integral I am interested in, okay, by definition of this integral given in the first line here. Okay, so for the second term, I have to work a little. For the second term, I have to work a little. The first thing we are going to say is the following. Here, I have a point between bti over n and bti plus 1 over n. So the Cin is a point, okay, between bti over n and bti plus 1 over n. I don't write the interval here because I don't know which one is the greatest, okay, in this situation. So I am just between bti over n and bti plus 1 over n. And I said that in this situation, this one can be written as the Brownian motion at a time that I denote by alpha I n, where alpha I n belongs to the interval ti over n, ti plus 1, excuse me. This one, okay? Why I have this? So the meaning of what I have written here is that if I have a point between the Brownian motion at the instant ti over n and the Brownian motion at the instant ti plus 1 over n, this point can be necessarily written as b of someone with this someone that between these two instants here, ti over n and ti plus 1 over n. And keep in mind that why I have this, but it's just a consequence of the continuity of the trajectory of the Brownian motion. Okay, if you have a mapping that is continuous, okay, by the mean value theorem, if it takes, okay, so it's the mean value theorem applied to the BT that is continuous. So just remind me what is the mean value theorem. In French, théorème des valeurs intermédiaires. So if you have f from R into R that is continuous, okay. If you have A that is equal to f, let's say, of x, that is strictly less than b that is equal to f of y, I said the following: for any C belongings to AB, there exists a Z belongings to R with F Z that is equal to C. So if you are a point between two possible images, all the points that are between the two possible images is in fact in the image of F. It is F of someone. So this is the mean value theorem, okay? And the mean value theorem is true if you have, okay, the continuity of F. And in the previous slide, okay, it's exactly what I apply here in the case of the Brownian trajectories that is continuous, okay? So if I am between B at some point and B at another point, necessarily I am B of someone with this someone that is between Ti over N and Ti plus 1 over N. Okay, so I have this one here. So I just remind the mean value theorem on this slide here. So in order to finish the proof now, okay, so what I have to do, so I copy this, okay, so excuse me what I have written here. So I have this, I have this, so let's do the job here. So I have proved that, so I erase this argument and I will plug inside here my B of alpha in, that is a point alpha in between Ti over n and Ti plus 1 over n. Okay, so we have seen together that this sum converges toward this integral, meaning that I have the beginning of the proof, okay? So now if I want to do the job, okay, I have only to be interested in this sum here now. And to prove that, my interest is to prove if this one converges toward the integral between 0 and t of f prime of ds ds. Okay, it's what I have to prove in order to finish the proof. Keeping in mind that this integral here is defined. So I erase this one that I don't need anymore. Okay, the limit I want to find here, this one is defined this way. So in other words, I will have to prove that this sum has the same limit as this one. Okay, and in fact, so you have understood what is the meaning of the Ito formula. I have proved you, okay, how to do step by step in order to approach this result. Okay, in fact, it's just a consequence of the Taylor expansion. Okay, simply, that's why I have the 1/2 in particular here. And in order to prove my result, it is sufficient to prove now that this one converges toward this one, okay, because the integral I am interested in, that is the last term in my Ito formula, this integral here is just this limit, okay? So the last technical step is to prove that this one converges toward this one, okay? So I won't do the proof of this one. I just want you to show this proof. It's a good exercise. Lectures note, page, what? Page 51 and 52, okay? But if I can give you an intuition about why this one converges toward the same limit as this one, but the fact is that, so alpha in is between ti over n and ti plus 1 over n, meaning that when n goes to plus infinity, these two are not very far, they are very close. The 2 points inside here are very close. And here, I know that in expectation here, the expectation of this term is simply ti plus 1 over n minus t1 over n. So in average here, this one is this one, and this one is not very far from this one when n is big, implying why, okay, it's not that surprising that the limit of this term will be the limit of this one, okay? So I won't do the computation in details, but you have then on the lectures note, okay? But what I want you to keep in mind, okay, for the proof of the Ito formula is that you discretize, you use Taylor expansion. At the first order, it gives you the stochastic integral here. At the second order, it makes appear the 1/2 and something involving the second derivative. And then by a technical computation, I can prove that I obtain this Riemann integral for the second term, okay? So do it at home. Have a look on this limit here. And if you have some question, I will answer on the live session of questions that we will have, okay, maybe next week. So see you next week, okay, to continue the course, and I will start the chapter 2 dealing with the Ito integral. And what we are going to do, we are going to generalize what we have done in the case of the Wiener integral and what we have done in the case of integral between 0 and t of f of bs dbs to more general integrants. And we are going to see that in this situation, we will generalize, and in particular, we will be able to generalize the Ito formula also. So see you next week for the chapter 1.